Okay, so this is our second video on analyzing graphs of functions, and what we're going to talk about here is increasing, decreasing, and constant functions. So we'll have a definition for each one of these, and then we'll look at a couple examples here. It's quite frankly fairly straightforward, but I do like going over the definitions. So, definitions here. A function f is increasing on an interval. Okay, come on, pen. Suddenly it's not wanting to write. So, function f is increasing on an interval when any x1, x2 in the interval has x1 being less than x2, implying that f at x1 is less than f at x2. And again, just to emphasize, what were we defining here? Increasing. And graphically, what you can interpret this is that the graph goes up from left to right. Now, the definition for decreasing is going to be very similar. So, a function f is decreasing on an interval when any x1, x2 in the interval has, and it's going to still be x1 less than x2, but instead we're going to imply that f at x1 is bigger than f at x2. So this is defining decreasing. And here the graph, whoa, it's an interesting way to spell graph. Come on. So the graph goes down from left to right. And so the one thing I want to point out here is this x1 less than x2 here, and this x1 less than x2 here. Now, the reason it's x1 less than x2 in both cases is this is really what's telling us that we're reading the graph from left to right. It's this second portion over here is what's defining increasing and decreasing. So that's why we have x1 being less than x2 in both cases. So one final definition here, and that's for a constant function. So a function f is constant on an interval. Man, spelling is just not going well with me today. On an interval when any x1, y1 in the interval has, Now this is actually slightly different. All we're going to say is f at x1 equals f at x2. We don't need to include the x1 less than x2 in this case, because if you're constant, it doesn't matter if you're going from left to right or right to left, because you're just horizontal and constant. Where the other ones, it does matter, because going up can be interpreted differently if you're reading a graph from left to right versus right to left. Okay, so those are our three things here. So we have increasing, decreasing, and constant. So let's look at a couple examples here. So these are just where we're going to be given some graphs and determine the intervals of increase or decrease. So determine the intervals where the function is increasing, decreasing, and constant. Okay, so let me go ahead and put a graph in here. Maybe. Did my graph disappear on me? Oh, there it is. Whoa. That was interesting. It's like hitting the print key too many times. I tried to paste it too many times. There we go. Okay. Man, I am just struggling here. We'll get this graph here in a second. Alright, there we go. Okay, so now I'm just going to sketch a function here. Now, I'm not giving you the equation here. I'm just going to sketch an example of a function. So, come on. And then I'm just going to label some x values. I'm just going to call this -3. And I'm going to call this, let's just call that 1. I know it might not be to scale, but we're just doing that for us being able to look at the intervals here. So now when I look at these, I just literally go from left to right on the graph and just see, am I going up, down, am I constant? Well, we can clearly see here, I'll bring out a highlighter. If I go from left to right and I'm highlighting the graph here, I'm going up. And I go up all the way until I hit -3, x equals -3, and then I'm going to go start going down. So I can write my first interval here. So I'm increasing on, well, I'm going from -infinity up to -3. Now we actually put a parenthesis with the -3. This point here has actually got a special term for it that we'll talk about in a second here, and we'll actually even come back to this same example. And then if we continue on here, now as I'm going down here, I can see I'm now going down, and I keep going down until I hit x equals 1. And so I am decreasing from -3 to 1. And then finally I've got one more interval here to look at, and it's going back up. And so I am also increasing from 1 to infinity. So I'd union this here. And this would be 1 to infinity. And so those would be my intervals of increase and decrease. And of course, there are no intervals where it's constant. Okay, so let's look at one more here real quickly. Okay, so let me sketch another graph here. And I'm going to do this one a little bit more to scale. And so this is -3, this is +2. And again, we want to do the intervals of increase, decrease, and constant. Well, again, I'm just going to kind of highlight here. If I start going from left to right, well, I'm clearly going up, so I'm increasing all the way until I hit x equals -3. So let's go ahead and write increasing. And the interval would be from -infinity up to -3. And then we can see here, from -3, I'm not going up or down, I'm remaining constant from -3 all the way up to 2. So I'm constant from -3 to 2. And then I'm going from 2, we can see I'm clearly going down. So I'd be decreasing from 2 to infinity. Okay. So next thing, and we'll go back to these examples here, but the next thing we want to talk about is what it means to be a relative maximum, and I'll put /minimum. So again, we're going to have a definition here. So definition, a function value f at a, so that's like a y value. This is considered to be a relative minimum. So this is what we're defining, relative minimum, of f when there exists an interval x1, x2 that contains a such that x1 less than x2 implies, I'm sorry, not just x1 less than x2, x1 less than x less than x2 implies f at a being less than or equal to f at x. So the way this is here, this x1 less than x2, we find some interval x1 to x2, then we're saying pick any point in that interval and we'll have that f at x is greater than or equal to f at a. Now the relative maximum is almost identical, so instead of writing it completely down like we did with the increasing and decreasing, I'll just put in blue here the relative max is the same, except we have x1 less than x less than x2 implies f at a is greater than or equal to f at x. Okay, so let's go back to these graphs here, these two examples, and see if we have relative mins and maxes. Now, what I like to think of it is just kind of drawing a box and seeing if it's a maximum inside that box. Because clearly right here, this point right here corresponds to a relative max. And this x1, x2, so let's say if you can draw some box around here, then inside that box, it's bigger than or equal to all the other y values. Now, the box doesn't have to be very big, it's just got to contain that point. So I could have made the box even much smaller here. In both these cases though, both these boxes that I've drawn around the point, we can see that it's a maximum in both cases. So this is a relative max. And then we can see clearly here that this is then a relative min. Now the next graph that we did is a little bit more confusing, but it really nails the definition here of relative max, because remember it was greater than or equal to. So if you look at this point right here, some people might think, oh, that's not a relative maximum because you don't go back down. It doesn't matter. If you draw a little box around that, and you look at this point right here, is this y value greater than or equal to all the other y values? And it is greater than or equal to all the other y values, because if I look here, these are clearly less than this point, and here these are the same, so they're equal. So this is a relative max. But similarly, actually every point along this constant line is a relative max. And that kind of makes sense. Just look at the graph here. Thus, in fact, not just a relative max, it's something that's also called an absolute max. Every point here on this constant portion is the highest that you can possibly get on the function. So they're all maximums. Okay, so that's important to realize there. Okay, last topic in this video here is we're going to talk about average rate of change. Of a function. Well, the average rate of change of a function is actually just the slope of a secant line. And what do we mean by secant line? Well, what we have here is that the average rate of change of a function from x1, y1 to x2, y2 is the slope of the line going through the 2 points. And that line just has a fancy name when you're talking about a function. It's called a secant line. So let's look at an example here. So what we have here is we're going to find the average rate of change of f at x equals x cubed minus 3x from x1 equals -2 and from x1 equals -2 to x2 equals -1. Okay, so I am going to go ahead and sketch this graph here. So bring up a graph. Okay, now this is going to be a relatively rough sketch, but it will give us a good idea here. So at 0, it's equal to 0, but I'm going to make this a little spaced out. So this is going to be -1, and this is -2. And then one of the x-intercepts is at the negative square root of 3, which is about right here. And then 1, 2, and then there's another one over about right here. And then, let's see here. this point right here. And so I'm going to do my best now to kind of sketch this. It's not very good there. Let me smooth that out a little bit. Okay, so that's a rough sketch of this. Now, what I want to point out here, I'll make this point a little bit bigger so it's on the graph there. What we say is secant line here, we're looking for these 2 points I plotted. Actually, I should plot a different point here. Let me just do something else there. Okay. -1 is this point right here. And then -2 is this point right here. So the average rate of change is if I draw a line, straight line connecting these 2 points, like this, the average rate of change is just the slope of this green line here. So the book likes to write a formula down for it, but I don't like to have to memorize a bunch of formulas. A lot of books like having lots of different formulas, but I like to just think about what the interpretation of this is. It's a slope of a secant line. It's a slope of the line going through those things. I already know how to compute slope. I just need the x values and the y values. Well, I have x1 is -2, so f at x1 is f at -2, which is simply -2 to the third power minus 3 times -2, which is just equal to -8 plus 6, which is -2. So I have a point, -2, -2. And then we also have on the graph f at x2, which is equal to f at -1, which is -1 cubed minus 3 times -1, which is -1 plus 3, which is 2. And so this point would be -1, comma 2. Now I have 2 points, and I know how to compute the slope, so my average rate of change is going to be 2 minus -2, y2 minus y1 over x2 minus x1, -1 minus -2. So this would be 2 plus 2 over -1 plus 2, which is 4 over 1, which is simply just 4. Okay, so we still have some more that we need to talk about with analyzing graphs of functions, but we'll cover that in our last video on this.